In this lecture, we're going to take a look at the general senses, those senses that are distributed around the body with relatively simple receptive cells or structures. So the general senses, they are associated with the skin, with the muscles, the joints, and the viscera, all of the organs in the ventral body cavities. And they include these senses: touch, pressure, stretch, vibration, temperature, pain, and proprioception. And we'll start by talking about touch and pressure senses. These are the sensory receptors that are involved here are mechanoreceptors, the ones that produce action potentials, or at least produce local potential changes that will stimulate action potentials as they are moved or deformed. And there are three receptor types associated with touch and pressure senses. The first are the unencapsulated dendrite endings. This is what we think of as the free nerve endings. So they're just dendrites that are specialized to be able to detect movement of those dendrite endings, and we find them throughout the body, especially in epithelial and connective tissues. And one of the more abundant examples are the Merkel discs that provide touch reception in the skin, especially around the hair follicle. And then, so we have the unencapsulated dendrite endings, and then there are the encapsulated dendrite endings. And these are dendrites that are surrounded or enclosed by a connective tissue structure of some sort. And again, most of them are mechanoreceptors. And the two most important ones are the tactile and the lamellated corpuscles that we've already learned about back in the chapter on the integumentary system. The tactile corpuscles, these are found at relatively shallow or superficial layers of the skin, especially in the dermal papillae, and they're especially numerous there in hairless skin, and they are what provide light touch sensations, and based on their abundance in hairless skin, are also a piece of what helps provide the erogenous zones of the body. So, the places that we stimulate romantically. So think the lips or the external genitalia. The lamellated corpuscles, also known as the Pacinian corpuscles, these are larger receptors that are deep in the dermis, and they're surrounded by layers and layers of connective tissue, and they provide the sensations of deep pressure and also vibration. And so they can respond to on and off pressures. So those are the touch and pressure senses. So the temperature senses, these are also provided by unencapsulated free nerve endings. And there are two types of receptors that provide temperature sensation: the cold receptors and warm receptors. And the cold receptors are primarily in the superficial dermis, and they are sensitive to decreasing temperatures. And their area of sensitivity is between, if I'm going to do here like a thermometer, a number line, they're most active between 50 and 68 degrees Fahrenheit. So we're going to just use Fahrenheit since that's the American way. And when we start getting down here into the colder regions, that's where pain receptors take over. And they're very abundant, about 3 to 4 times more abundant than warm receptors are. Warm receptors are located deeper in the dermis, and they're sensitive to increasing temperature. And they display the greatest sensitivity between 77 and 113 degrees C. So let's add them here. So this is cold reception here between 50 and 68. And then at 77 up to about 113, give or take, we see warm reception. Notice that though, and then as we get higher than 113 degrees, up here, that's where pain again takes over. So in both cases, as we get outside of this range, the cold receptors stop responding, and if we're getting very cold, then pain picks up. And again, with this range here in the warm end, as we get warmer or cooler than the range, then again the receptors stop responding, and if we get up into the really warm temperatures or hot temperatures, that's when pain begins to take over. But notice, interestingly, that there is this zone where there's no where no receptors are getting excited. Here between 68, I forgot to write this in, 77 degrees, and here's 113. So we have this zone between 68 and 77 where there is not a whole lot of stimulation coming from either the warm or the cold receptors. And think about this. This is where room temperature is. So if we're thinking about in our skin and how we like to be comfortable, we are most comfortable when there is no information coming from either the warm or the cold receptors. On the other hand, think about the things that we like to drink. Anybody, well, I think I should be here on this, yeah, so I got this confused. I should have moved on to the next slide, and I forgot about this. So let's put this in here again. We have 50 to 68, and then 77 to 113. So we've got this zone of no stimulation here between 68 and 77. And so think about how you like to have your beverages served up to you. We generally either like to have them as cold or as warm, somewhere up here in the warm ranges. So in neither case, for beverages, are we interested in this, in having, what we think of as these lukewarm temperatures. So nobody is ever going to order a big old tall glass of kind of no temperature sensation producing milk. So there you have it. A little bit of explanation for why we prefer the temperatures that we prefer in our environments, where we're living and where we like to hang out, and with the beverages that we like to consume. So we want to get some kind of sensation from our hot chocolate or from our iced tea that we're drinking, not to have this no response at all inside the mouth. Okay, so that's it for warm and cold. Let's think about pain. Pain is provided through, again, free nerve endings, and there are millions of them found throughout the body. The one place that we don't see pain sensations being generated is in the brain. My mother-in-law, not recently, she's passed away now, but she was having some brain surgery. She had Parkinson's disease, and they kept her awake and did not want to, make her so sedated that she couldn't respond while they were doing some work. They were trying to stimulate the substantia nigra, the area that produces dopamine, that stops producing dopamine in Parkinson's patients. But they kept her awake, and they didn't have to do any kind of numbing to the brain because there are no sensory neurons there that are going to notice pain. So they had her opened up and were sliding these electrodes down through her brain tissue and talking to her the whole way. And she reported that, she had some weird experiences, memories, and sensations, but none of it had to do with pain. And pain receptors are stimulated by any of the things that actually damage tissue. So heat, cold, twisting and pressing and squeezing kinds of pressures, and anything that damages the tissues is likely to stimulate pain sensations. And of course, pain has a very adaptive function. We need to know when we've injured ourselves so that we can take corrective action, stop doing whatever it is, or tend to the injuries. And so it makes sense then that that pain receptors tend to adapt very slowly to constant stimulus, if they adapt at all. So for most people, pain doesn't adapt. And so chronic pain is a big deal for people who are experiencing especially neurological damage, or have had some really serious, like a car accident, something that really damaged the bones of the body and got structures knocked out of alignment. So that kind of chronic pain is a real issue because pain receptors frequently don't adapt. And we can classify pain signals based on where they originate from. If it's from the periphery of the body, then that's somatic pain. And if it's coming from the organs, then that would be visceral pain. So somatic pain, it originates at the skin, the muscles, and around the joints. And two kinds of somatic pain. Superficial somatic pain, this is the sharp or prickling pain, usually short-lived, because they're carried on type A fibers, the fast pain fibers. And so the source can generally be localized to directly to the affected region. For instance, I had a couple of vaccines. I'm getting ready to head overseas, and I had a couple of vaccines, and I know exactly where those needles went in because of superficial somatic pain. Deep somatic pain, on the other hand, is indicative of tissue damage. It provides aching, burning pain, or sometimes itching sensations, and tends to last longer, and this is slow pain. So the location of the source of the pain can sometimes be difficult to locate, to actually, point out. So, so joint pain would be an example of deep somatic pain, when you have this aching, burning kinds of sensations, that, generally joint achiness, and because of inflammation, say, in the joint. Visceral pain originates from damaged tissues in the organs in the thoracic and abdominopelvic cavities, and it's the only conscious sensory reception that comes from the viscera is visceral pain, and it's generally felt as aching, gnawing, or burning sensations. And again, carried on slow pain fibers, the type B fibers. So there is a really unusual characteristic associated with pain, and that is what's termed referred pain. And these are pain sensations that feel as though they originate from a different location in the body than where the pain stimulus is really coming from. And referred pain is characteristic of visceral pain. And so there are some classic examples of referred pain. One of them is what we associate with a heart attack, where not only do people feel a tightness in their chest, but there may be pain radiating down the left arm. Kidney pain can be referred around the waist and down both the inner and the outer thighs. And liver and gallbladder pain can be referred to the right shoulder. And so it's important to know about referred pain and to understand how pain can be referred, because frequently you can have patients who are talking about pain in a very particular way that doesn't make sense. Well, why would and it could be because of referred pain. And so on page 448, figure 12.2 is an image that shows some of the locations of referred pain, and you can see some of the diagrams there. So the yellow area is kidney pain, where it's referred around the waist and down the inner and outer thighs. The liver and the gallbladder with their referred pain up into the right shoulder and neck region. And it occurs because the afferent fibers that are carrying visceral pain travel along the same pathways as the somatic pain afferent fibers that are bringing in information about somatic pain. And sometimes the brain will, in these kind of cases where referred pain occurs, the brain confuses these visceral pain transmissions with somatic pain transmission. And rather than projecting the pain back to the source, it projects it back to these referred pain locations. And it turns out that pain that originates from parietal membranes, so pain originating from visceral membranes, it can be referred, but usually the parietal membranes do not experience referred pain. Okay, so pain nerve pathways. Again, there's the A fibers or acute pain fibers or fast pain fibers. They all mean the same thing. These are fine, very thin myelinated fibers, and they transmit pain sensations very quickly, between 12 and 30 meters per second. So that's something on the order of 40 to 100 feet per second. And we associate it with sharp and prickling pain felt at the skin surface. So again, like something poking or cutting, those are sharp and prickling pains. And they tend to stop transmitting when the stimulus is removed. So once you stop poking at somebody with a little sharp probe, then those acute pain fibers will stop sending pain messages. On the other hand, chronic pain, C fibers or type 2 fibers, slow pain fibers, all these things mean the same. These are small but unmyelinated fibers, and they transmit, because they're unmyelinated, they transmit their sensations much more slowly, between a half and 2 meters per second, so something like 1.5 feet to 12 feet in 1 second. And we associate the pain sensations carried along chronic pain fibers as with dull and aching pain sensations. And these, even when you remove the original stimulus, they will continue to transmit pain signals for quite a while. Regardless of whether it's chronic or slow pain, all pain fibers synapse with interneurons in the dorsal horns of the spinal cord, and their axons are decussate, and then they transmit on, up the spinal cord, through the medulla, the pons, and into the thalamus, the hypothalamus, and then onward into the general sensory cortex of the brain. So pain threshold and pain tolerance, these are two different ideas. Pain threshold is the amount of stimulus required to initiate an action potential. And so this is pretty much the same for every person. But not every individual has the same pain tolerance. And here, when we talk about tolerance now, we're talking about perception. So pain threshold, that's what creates a sensation, a action potential traveling along a axon. Pain tolerance, on the other hand, is about perception. And so individuals vary in their interpretation of the intensity and the origin of that pain. And pain tolerance is requires or relies on both the intensity of the signals that are being sent and where it's coming from. And based on emotional state, the limbic system can actually modify how much pain we experience. As well, pain tolerance can be affected by whether that pain is long, chronic, ongoing pain. The longer pain lasts, the lower our tolerance to it generally becomes. Age can be a factor, so young children tend to be less pain tolerant than adults are. Cultural factors can play a role. So if men are supposed to not feel pain, then we can be trained, and cultural factors can kind of help to modify how we experience, how we interpret and perceive pain. And then finally, psychological factors can have a role. So when one is under extreme emotional stress, then frequently people can be severely injured but not feel any pain. And so this is, the soldiers who've been injured really, really badly, but they're kind of wandering around in a dazed kind of state, as an example of how psychological factors can play a role. So pain threshold and pain tolerance are two different ideas. Threshold, anytime we use that term threshold, what we're talking about is how much of a increase in polarity, how much polarization has to recur in order to stimulate an action potential. While tolerance is a very different concept. This is how we perceive the pain, and it can be heavily influenced by a number of factors. Okay, so now the last of the general senses is proprioception. Here the receptors are encapsulated, so there's a connective tissue sheath that surrounds the receptors, and they provide information to the central nervous system about the length of and the tension in skeletal muscles and tendons. But, and this is interesting, they don't cause perception. So we don't have conscious awareness of this, but we have unconscious recognition, and we can respond accordingly. And there are two primary types of proprioceptors. There are the muscle spindles, and these are located in skeletal muscles. They're composed of between 3 and 10 what are termed the intrafusal fibers. And if you look on page 451, you can see an image here of a muscle spindle in a muscle. And they are stimulated by stretch in the muscle. And what they generally do is stimulate a stretch reflex, which causes then contraction. And this helps to maintain limb position, maintain body posture. So we see these muscle spindles involved heavily in maintenance, in reflexive maintenance of body posture. The Golgi tendon organs are found in tendons, and they are found near where the muscle attaches to the tendon, and they're stimulated as muscle tension increases, again stretching, pulling on the tendon itself. And they also initiate reflexes that will, rather than stimulate contraction, will inhibit muscle contractions. So as we begin to overstretch a muscle or a tendon that's associated with that muscle, then the Golgi tendon organs will inhibit the muscle from being able to contract. And again, it helps as a means of maintaining posture, and helps also to protect those muscle attachments, so to protect the tendon where it attaches back to the bone, and prevents it from pulling on our bones so hard that we rip away the tendon from the bone. Generally, it protects against that. Okay, so there we have it. The major senses, or the kinds of receptors that are associated with the general senses of the body. As always, if you have questions, get a hold of me.